Now, after we have covered log analysis and how we can investigate our logs further to find suspicious activities, dive deeper into the information and gather all the aspects of the attack and connect them together. Now we'll look at how we can do an in-depth investigation. So we have found that these machines are suspicious. Probably there's something happening in these machines. How we can investigate further? We can use our digital forensics, malware analysis, and memory forensics to investigate the machines further and answer very important questions. How the attacker came here first time? What exactly he's trying to do? What are all the indicators of compromise on that system? Indicators of compromise can tell us are the kind of signatures of this attack. Could be the malware hashes, could be its own domains or IPs, registry entries that have been changed, and so many different things. And we can go from this investigation to understand what is the malware capabilities and how much it gives to the attacker, how much control it gives to the attacker. And we can do all of that through malware analysis. So the live forensics, we can look in the network part to see if there's unusual ports are open, unusual network activities, processes that we don't know that does something, or processes that should not do this network communication or network access, network HTTP requests or whatever, and we look for anything that's suspicious being sent and received through the network. This is the network part. The memory part, we can look for unusual processes, applications that are running in the system that we don't know about. For maybe not all the processes are legitimate, but there are unknown libraries being loaded inside of them that maybe are not in the system, not in system 32, but they are in different paths, writable paths by the user, something like application data, documents, whatever the place that might have, whatever the folder that might be writable by the user. Also, the temp could be a good path. We can look for libraries that doesn't have the DLL as an extension. It has the temp, something else that looks unknown. We can also look, maybe the malware is not didn't load another library inside the process, but it used process injection to put some code inside another legitimate application and execute that code so it can remain inside this legitimate process real. We can look for this suspicious allocated memory, see if there's any memory allocation that is read, write, and execute, or writable or readable and executable. And as well, it's a private memory. It's not a memory that is being part of any process or any library memory. We can look for something like that. We can even do a full memory analysis and see if there's any process been terminated and looks suspicious, if there's any suspicious strings, any suspicious commands have been executed on the shell, and so much of information. Apart from the memory forensics, which can give us lots of information about the attacks, especially nowadays with the fileless attacks, we can look for forensics artifacts, something like prefetch, shim cache. There's so many different what's called digital forensics artifacts that we can look for any clues about what had happened in the system. We can know what are the applications have run on that system and when the first time they have run and the last time they have run on that system. We can see all of that through prefetch. We can see all the persistence all the different places that the malware can maintain persistence through, whatever, through scheduled tasks, through registry keys, through different opportunities, and you can see all of that through autoruns and other apps. We can also look for any USB drive that has been attached to the system, when they have been attached and why they have been attached. We can look for so many different artifacts inside the system to see any clues of something malicious had happened. We can look for URL history, emails that are still in the disk, some evidence of emails inside the disk, documents have been opened, the last files have been accessed. So many things we can look for in the forensic artifacts. We will go into a demo very soon. But the tools, just want to mention the tools that you will need to have in order to replicate this demo. The first is Wireshark or Microsoft Network Miner. System internal tools. We will use Autoruns out of as one of the tools from System internal tools. The Process Hacker, it's a really great app, and an optional, you can use WinBMem to take a full memory dump and investigate that using volatility. So now we'll go into a demo, a live forensics demo, and it's actually a real example of a real malware have been executed on a machine. We are seeing this machine is behaving suspiciously, connecting to unknown IPs that are not associated with any legitimate domain, and we want to investigate further why this machine is behaving that way. So we will go now to that demo. So in this demo, we'll take a look on how we can perform a live forensics, a live investigation. This investigation could happen after we detected that this machine is performing something suspicious. Either we detect it through log analysis, network behavior, or through the host behavior using our endpoint detection response, or sysmon logs, or Windows system logs. This demo as well can work, and the same techniques can work if you want to check your personal laptop, if you think that there is something suspicious happening in your laptop and you want to investigate further. We will start with the network analysis, see if there is any network communication that looks suspicious. We can go we can use Microsoft Network Miner. If you don't have this tool, I recommend you to install it. And this tool works as a combination of Wireshark and netstat. With netstat, it tells us which process is connecting to which IP, and Wireshark, it shows us exactly the packets being sent and received. Network Miner is doing basically both. It shows us the process that do the communication and as well the network information. So let's look at a simple example. We create a new capture up here and we click Start. Now the tool will start to capture network activities, and we will see if there's anything suspicious happening. We see some networks that there's no process name, which means it's just performed by the system. We see something else is being performed by an application called DNT. We don't know what this process is actually doing, but it is performing something. It's connecting to the internet to the IP 37.187.72.193. We don't know exactly what is that. We can see here the frame details that tells us more about what's happening in this communication. We can see it's an IP4, it's a TCP, of course. We can see here in TCP, he's communicating, the source IP is random, but the destination IP is 8080. So it's connecting to this IP on port 8080, and the communication is just some random bytes. It's not an HTTP request. It doesn't look like something recognizable. So this is something we need to investigate further. Might be in HTTPS, probably, but we don't know. And this app doesn't show much as Wireshark, as you can imagine, but it gives us the ability to see all the traffic up here. You can see here this app that we don't know exactly what it does. We have Microsoft Edge, we have the system, Surface apps, and as well, again, Microsoft Edge. As you know, Microsoft Edge and Chrome, they have multiple processes running at the same time. They run so many different processes with the same name. So that's why you see multiple Microsoft Edge up here. The system traffic, it also represents the surfaces. So don't say that, okay, this is system, this is not suspicious. They might be suspicious as well if it's a service that's performing that behavior. Microsoft Network Miner will not help you to know exactly which one that does the communication, but a further investigation can help us. For now, we'll focus on our task, and we have here a file that we don't know much about. We see that it does communication to 37, to the IP 37.187, and we see as well on 74, 209, we see so many different IPs it's trying to connect to. This is our first step, and we really saw that there is some suspicious behavior that's happening on that machine out of this unknown process. We can do exactly the same thing with Wireshark and Netstat and see these packets in details. I don't recommend you to open both applications at the same time because both will be capturing the network traffic. But you can use Wireshark and Netstat, or you can use Microsoft Network Miner for connecting the process list and the network traffic. So that's the network level. We have got our first investigation. We have seen already so many different IPs that could be IOCs. We can investigate them further through looking at reverse lookup on the IP, so we can know if it's connected to any known domains. We can check in VirusTotal to see if this IP is already known as suspicious. Mostly VirusTotal is not very reliable with domains and IPs, but still a good source. As well, in VirusTotal, it can tell us a bit more about if it's connected to domains that has been there on VirusTotal or not, which can tell us a bit more about the IP and its connection to different domains, these domains and connection to different IPs, and so on. But for now, we have a list of IPs that can we start with, and we can save them as potential IOCs. We can investigate as well in our logs to see if there's any other machines that are connecting to the same IPs. So that's for the network forensics part. We'll not save it for now. For you might need to save it. And now we need to investigate the processes and what's happening inside the memory. We'll be using a tool called Process Hacker. And Process Hacker basically replaces your task manager after you install it and add it as a replacement for task manager. If we click up here into task manager, we will see, give it a second, we will see that it will open Process Hacker and not the task manager. Here's our Process Hacker. And Process Hacker is really a great tool to see all the relationship between different processes, see if there's something suspicious is happening, as well as investigate each process way further. Let's say we can ignore all the services part and we look at any application that run under Explorer. This is the application that run under the user, mostly under the user himself, and see if there's any suspicious relationship is happening. You might see Word process opening PowerShell and PowerShell is opening another process, and we see a suspicious connection. Also here, he can point out to see if there's something looks suspicious, and here he's seeing that this app, the CNT, which what we saw in the network miner, is marked as suspicious with this red pink type of color. We can investigate this process further and see what exactly this process is. We don't know where it came from, but we can see that this process is performing something suspicious. With this app, it can tell us a bit more about where this file is, so we can take a copy of it, get its hash, use this hash as a lookup. As well, it can tell us some information. We can see here the threads that's being running. We can see all the files are being opened. If we see an app that's opening so many different files, that's something suspicious and could be a ransomware. For this one, we don't see that, but we see different Microsoft, different registry entries that is trying to access. Many of them, many of them will not be suspicious, will be system perform like a normal thing to have, running by different Microsoft libraries. Some of these handles will be opened by different Microsoft libraries and not exactly related to the malware behavior, but some things might be related. And we see so many things related to Internet Explorer. So he might be trying to access Internet Explorer and know more about it, maybe inject inside it or change its own settings, and so on. So we see lots of registry files, any type key is a registry key, and we see so many different things have been accessed here, some related to internet settings and so on. And we can see the threads, the files up here. There's only one file being accessed, so nothing really suspicious and something related to the system. We can also go and see the loaded modules up here. And with loaded modules, we can look at if there's any suspicious library. Of course, this is if that's exactly the model of this process. It's not really important to look at what's exactly the loaded library. But if we think that, let's say, Internet Explorer has some malware injected inside of it, or Microsoft Edge or Google Chrome, then we need to investigate the library, see what might be injected inside, what's the library that might be loaded and not related to the actual legitimate application. We can take a look here at the memory, see if there's anything suspicious. And the most important up here, just to make it smaller and easy to access, we can look for strings to look for if there's any things that look suspicious in the memory. Here we'll look at only the privately allocated memory, either by the app or either by the application itself, memory here allocated to save some information, or by different libraries. This memory will not be mixed up with so much from the library's text. We have inside of here so many different, if we look at modules up here, we see so many Windows libraries have been loaded, and all of them include so much of text that we don't need to bother with. So we will look only at the private memory to see if there is anything suspicious up here. In the string search is trying to find text or find letters, bytes basically, that represents a text. And in most of these type of searches, they might see lots of garbage. They might look at some bytes that represent some code, and the app, see it, Process Hacker or any other app that try to extract strings, he might see these bytes as actually text. The best way to decrease garbage is to increase the minimum length of the text. So if we put it as 10, then he has to give us text that are 10 bytes or long, or 10 characters and longer, and that can decrease a lot the garbage that might be or the data that might be misinterpreted and being seen as a text, which is not text. It might be some code or some random data somewhere, and he saw it as a text. So we click on minimum length 10 and click OK, and now we see so many different text up here, and we can start look into this text and try to understand what this text represents. So some are registry entries, some might be related to the Windows system libraries. We see here the history might be related, might be not, and some other information. But here we see referrer and then a suspicious IP, and looks like an HTTP request. So this is something that look quite suspicious for us. Similar here, we see this IP. We see, if we go down, we see a file name up here in the documents. We can investigate further what is this file name and what it represents, and if there's actually a file in that place or not. We can go further and see if there's anything that looks suspicious. These texts, as you see here, are mostly the Windows environment data. You don't need to care about like the path, the operating system. This is mostly being saved inside the memory, in private memory in so many places. So we can ignore that for now. And we can go further to look for if there's anything suspicious happening on the system. We saw one domain until now, and we can go further and see if there's any other domains or any other thing suspicious. We see this random paths over and over again. We see here a file in temp, detector trace, maybe that's a log file he's saving up here. We can investigate that further. we can start to copy this information that looks suspicious inside the text. We can copy all of that text and start to filter it out, searching for data like HTTP, we can use some regex to investigate further this and extract IPs, extract shell commands, extract registry entries, extract file paths, especially in temp. And we see here another IP with HTTP type of header, like content length, connection, keep alive, and so on. So we see that this might be a connection has been made with that IP, and he's sending an HTTP request. We see, and we kind of see more of this. This is just paths. We see more IPs and more URLs appear. This is the name for a Windows library that used to communicate with the internet through HTTP protocol, as has been seen from the name. And there is so many different links, internet settings, so you might be looking for Internet Explorer, and so on. And we can investigate that malware further. And now we have so much information inside the memory. We have so many IPs. We have so many HTTP URLs, full path. Sorry, this one. Full path like this one. We can even collect all of this information and use them as an IOCs we have seen inside the memory. We see here so many different IPs and HTTP communication and similar URLs here and there with the IP 8080 or the port 8080 or port 80 or even port 443 to communicate through HTTP, not HTTPS, and we see that through the whole data. This could be a really good investigation to understand more about the malware. We have now detected that this looks very suspicious. We can dump the whole process memory to investigate further on our own time. We just create dump file, and he will save that dump file for us. We can save it on desktop up here, and we can take this memory dump and investigate it further, extract more information on our environment that we use for on our lab. If we are using a lab to extract information and do more analysis, we can find the file itself and try to take a copy of that file and try to reverse it on our own lab. That's for this analysis. We can do more than that. We can go to Microsoft Edge and look for if there is any injected memory, if there's any injected library. We can look at the modules here and see if there's any module that look, the computer is a bit slow. We can look here at any module that looks suspicious. Inside of here, we see some unknown modules up here. We see some stuff. We can investigate that further. We can also go to memory and try to find any read-write executable memory. Most of the malware, they try to inject inside different processes, and when they inject inside of them, they try to allocate a private memory that's read-write and executable. So the malware can run there and modify itself if it needs to modify itself, unback itself, reload itself, and continue the execution of that malware until it's being fully injected inside or fully loaded inside this legitimate application memory and getting executed in its own thread. We can look for private memory that's actually read-write or an executable, or even just read an executable. We can look here for any private commit or private to see if there's any one of them that has the protection read-write executes or read executes, and see if there's probably the malware tried to inject inside this process. We can check other Microsoft Edge process because we have multiple ones. And we can as well investigate if the malware is doing has tried to maintain persistence, where it ran first time, what are the all suspicious files that have been run at the beginning, when this malware started, and so on. The next step for us, now we know the malware, we have extracted the malware, we have seen its network communication, we have extracted so many IOCs, we might have copied actually the file itself, and we have the memory dump of it. Now we need to go backward to understand how the attack actually happened in the first place. One of the ways we can look for that is to look at the Microsoft prefetch. Prefetch are basically files created by Windows. Every time a process has been executed for the first time. When you run an application, whatever the application is, Windows try to make this application run faster next time. So it saves some information about how this malware starts, what libraries does it load, and some information that helps Microsoft to load this app faster next time. This Microsoft does that for all apps you have run inside your system. And they save these files, they save this information about each process in a folder called Windows Prefetch. And with this folder, we can see when the application has run first time and when it was run the last time. We see that every time Windows modified this file, we can see that the modified date represents the last time this malware ran, and the created date is the first time this malware has run. And we can see if there's any other files that look suspicious that run close to the first time this malware has run. So we can go here to see Windows and go to the folder Prefetch. And of course, it needs administrator privilege to be able to access that folder. We click Continue. This is part of what they call it digital forensics. Digital forensics is really a big science and was created mainly for crime investigation, but then it used as well for cybersecurity attacks. And with cybersecurity attacks, we have so many clues that we can look for inside the system to know more about the malware, know how it came first place, what commands the attacker has executed, and through any activity the attacker is doing, we see he leaves evidences on the desk that represents these activities. One of them is the prefetch. So we have here the app called DAVCINT. We can look for that one. Up here, we see that this is the first time has been executed, and it was executed. If we check the created and modified time, we see that it only has run once because the created and modified time is exactly the same, and it has been executed on March 21, 2021. So that represents for us that this is the exact time the malware has actually started. And now we can look for files that has the same modified date. Why? Because there might be other applications that run very close to that time that might be the beginning of that malware, might be the dropper, or might be the word, the word.exe or excel.exe that can tell us, might be that this is the time when this malware has been executed. Of course, with the legitimate application, it might has been used later and later, so we cannot really find that so much from the prefetch. But if there is another malware that it was a dropper, we can find when it was there and which malware has actually dropped it. So let's check with modified date, and this is when this file has been executed first time and last time as well. And we see here that there is another file that looks in a very suspicious name, has been executed at the same exact time. It's exactly the same time as this one on 3/21 in the same exact minute. We also have seen that name inside the strings of this file. When we looked at the strings inside the memory of dav cint, we have seen this file name as well in the memory in the documents. The actual story, what had happened is that I executed that malware 6229915.exe in the documents folder. It deleted itself and it dropped that malware in the application data. So this is actually a good story or a good investigation to find that there was a file has been executed on the system. We don't know exactly what is this file, but we know that it has been executed at the same time, the same exact minute as the diff client.exe. And that could be a really good case for us to investigate further, look at the deleted files and try to reach for that file if it's on the system, if it's still on the system. That's for going backward, and there's so many different ways. We don't have time to really go into the whole digital forensics part, but the last thing I will look at is if this malware is maintaining persistence. Does it maintain persistence or not, and how it maintains persistence? There is a very cool app created by Microsoft. It's a Microsoft System Internals. It's called Autoruns. We can find it, I believe, in the behavior analysis. And here it is. So Autoruns shows us all the applications that run at in the startup of the system, all the applications that get respawned again after it's being terminated through either some registry entries that makes this application runs every time in the startup, or it runs with another application, or it's being injected inside another process. It tells us all the applications, all the libraries even, that's being respawned again after they have been terminated. And this is the exact behavior that a malware is trying to do to make sure it keeps its own persistence on the system. So after you restart the machine, after you terminate it, it's able to rerun again. So you can click on Autoruns, agree, and then it will take a little bit time to load. By the way, my laptop is very slow. I'm really planning to get a new one. And you can see here if there's anything that looks suspicious for us. He doesn't recognize these two libraries. That's a good start to investigate further. Might be something malicious, might be not. And you see multiple of them in the session manager known dealers. And we can search for this dev init inside all of them, search if it has been trying to maintain persistence anyway inside. We can see it's actually here. In the current version run, we have OneDrive, which is a normal Microsoft application, but we also see dev cint is trying to also load, and this path, the Microsoft Windows current version run, is one of the most known registry entries for the malware to maintain persistence. This path is basically a path that Microsoft checks every time the system restarts, and it runs all the applications being saved under this registry key. So it checks that path and then runs this application from this path, run OneDrive through this path, and runs all the application one by one at the beginning every time the system starts. Malware has been abusing that registry key for so long time, and every time they write their own malware inside of here, and as well the path for that malware, so we make sure that they maintain persistence on that system every time it's being rebooted. So we have found that this malware is maintaining persistence through this registry key, and this is one of the things we need to add as a suspicious activity. Now we have collected the IOCs. Now we know that this machine is for sure is infected, and this malware connects to so many REPs that we're able to extract them through the memory dump. We know that as well. It's a malicious file. We can try to extract the original file has been dropped in the documents, and we can go through the whole malware analysis process as well to understand what's the capability of this malware and what it exactly does. So I will leave you here with that demo. Hope it wasn't too long, and see you in the next part of this module. So I hope you enjoyed the demo, and now we'll end this module with the recommended books and resources that you can learn more. The first one is Applied Incident Response. It's really a great book. I totally recommend you to read it. It's a new booklet, relatively new. It has been published back in March 2020. I really recommend you to check it out. Also, there are different resources that are very useful for you to learn, to practice. One of them is EVTX attack samples, and they are event logs that has been collected with in different attack scenarios, from initial access, from privilege escalation, from lateral movements, different attacker events that the attacker has done on suspicious on some machines. They have collected the logs that have been saved at that time, and they have categorized them with the meta attack categorization. So if you want to know how to find if the attacker is trying to steal the credentials on a system or is trying to escalate privilege, you will find folders inside this EVTX attack samples, and you will see event logs that are just recorded for that event. So you can check them out, run your queries on them, see if they make sense, see if you find something suspicious on them, and learn with them. Another good resource is Splunk searches and security content tree develop detections. In this folder inside the Splunk security content, you can find so many different Splunk searches that are useful to detect different activities. Each one is included inside the folder, inside the file, and this file says exactly what this search is trying to detect. You can use these searches along with the EVTX attack samples to make an understanding of how to detect this specific technique. You can also take from this EVTX attack samples different event logs related to the attacks that you see in real life, the attacks that might target your organization, and look for how this can be detected, if these searches make sense to detect them, what are the false positives. Run these searches in your own systems. If you are working in an organization, run these searches on your system, see if you find something suspicious, if there's too much noise, how you can improve it, how you can filter out, and how you can still detect the attacks through these attack samples that are there, and that will help you build your own library of searches, of queries that helps you detect suspicious activities. Last but not least, there is a Splunk attack range, and this is really good if you are learning incident response by yourself or inside an organization. You can use this attack range to actually deploy an infrastructure of a small lab infrastructure that looks like a company with a domain controller with different users, and you can see that how the attack is being performed on them using Caldera that we have described in the previous module, and how you can run different Splunk queries to detect this attack by scanning the logs and detecting these suspicious activities on these systems. So it's helped you to practice the defense, help you to see how real attacks look like with this Splunk attack range. So it's very good for practicing blue team or red team. You can use this infrastructure to try to hack them by yourself manually, see how Caldera has hacked them. You can try to scan the logs and wear the blue team dress, let's say, and try to see if you can detect these attacks or not. So I will leave you with this and see you in the next module. Bye bye.